Hello and welcome back to SSL TLS lecture series. This is part 4 and I am Saravanan learning along with you. In the last episode, we discussed about the stream cipher, right? So I gave RC4 as an example of stream cipher. I also mentioned that the stream cipher was designed by a famous cryptographer called Ron Rivers of RSA Security in 1987. This RC4 is called reverse cipher 4 and sometimes it is also called as Ron's code. When you look at some of the older documentation, right, instead of RC4, you will see the word called ARCFOUR, ARC4. The reason is, initially RC4 was trademarked and patented by RSA Security, and sometime around in, I think in September 1994, the code of the RC4 was leaked on the news group, and initially RSA did not confirm that the leaked code is their own RC4 code. Then people also wanted to avoid the trademark problem with the RC4. So when they wanted to implement the RC4 to avoid the trademark problem, they decided to use the name alleged RC4, and hence they end up with a new word called ARC4. So if you look at Microsoft documentation and other older documentation, quite often you will see the word called ARC4. So that's how we ended up with a name called ARCFOUR instead of RC4. Okay. Then apart from the SSL TLS, it is also used in the Wi-Fi protocol. In the Wi-Fi, we have a protocol called Wired Equivalent Privacy, and later another standard came because web was broken. So the later another standard came called Wi-Fi Protected Access. So both of them uses RC4. However, due to security reason, nowadays both the protocols are banned. You should not use web or WPA. So if you are using wireless, you should only use WPA2. WPA2 has a different protocol called Counter Mode CBC MAC protocol. It's called CCMP, Counter Mode CBC MAC protocol, which is nothing but internally it is using AES protocol. Okay, so we don't go into the details of all these things now. It is also extensively used in SSL TLS for a very long time because it is very fast. I told you, right? Stream cipher is usually fast compared to block cipher. In particular, RC4 is very fast both in hardware as well as in software, and hence it was very popular with SSL TLS. But later they found security holes with RC4, and finally in the year 2015 they came up with a new RFC called 7465, in which they completely prohibited for all versions of TLS. So if you are using SSL TLS, you should never ever use RC4 going forward, okay? Because of the various weakness with RC4. Okay. Next, let us look at the block cipher. So what is a block cipher? Unlike the stream cipher, in stream cipher I told it will always take one bit or one byte or one word at a time, right? In block cipher, instead of one byte at a time, we always take a bunch of data. For example, we call it one block of data at a time. You can define usually the cipher will define the block size. The commonly used block size in the past was 64-bit and 128-bit. Nowadays, we are no longer using the 64-bit. We are mostly using 128-bit block sizes. Okay. Now you will have another question. What if my data doesn't exactly ends with 128 byte? Let's say I have few more things here. In those cases, you have to add the padding so that the block can be multiples of 128 bits. Okay. So if needed, if your input size is lesser than 128 bit, you have to use padding. So all those things we will see later. Okay. So the next thing we wanted to see is what are some examples of block cipher? There are lots of block ciphers are there. There is something called Digital Encryption Standard. There is a variation of this called Triple Digital Encryption Standard, 3DES. And then we also have something called Advanced Encryption Standard. Okay. So in the 3GPP communication, if you are using mobile, right, in mobile we have something called 3GPP standard. So in the 3GPP communication system, I told you in the previous episode, when you use the when you use the GSM, right, in the mobile, GSM initially started using A5 bar 1 and A5 bar 2 stream ciphers, right? I told both of them are no longer secure. Whereas in 3GPP communication, they decided to use a block cipher called A5 bar 3. It also has another name called Kasumi. Okay, so we don't go into this. Then the Japanese government decided, why don't we have our own block cipher instead of using what is created by American government. So they went ahead and created something very equivalent to AES. Almost it is very equivalent to AES in terms of security. They call it Camellia cipher. So within it is not very popular outside Japan, but if you are in Japan, this Camellia is a allowed standard to use in the government departments in Japan. Then the South Korean government, they also created their own version, something like AES, which provides equivalent security of AES, called ARIA, ARIA. So ARIA is actually came from South Korea, whereas Camellia came from Japan. But most of the time you will only see nowadays this AES. Okay. There are also numerous other block ciphers such as Blowfish, Twofish, etc. We will not have time to go through all of them. Okay. Now let's start with DES. Let's see some story from the history. It's not story, it's actual history. In the beginning, right, during the cryptography was developing, none of the government will trust each other, and they kept all the algorithm that they were using for encryption, decryption, everything as a secret. Even during the World War time, none of the algorithm were published. Everything they were keeping secret. But a big revolution happened sometime around 1972. Until that point of time, all the governments were protecting each other algorithm, so that they thought by protecting the algorithm, it will be much stronger. But the American government did a big revolution. In the US government at that time, there exists a standardization body called National Bureau of Standards. Nowadays, it got a name change. Now it's called National Institute of Standards and Technology. Okay. So these guys, the NBS guys, they made a revolution in the history of cryptography. So what they did in 1972, they made a call for proposal for a block cipher. The purpose is to use the block cipher in all the application, including the military application, federal government application, as well as the e-commerce application, etc. So throughout the world, lot of cryptographers started submitting their own algorithm for this competition. So a lot of people submitted. Among them, almost after 2 years, sometime around in 1974, they finally chose the algorithm submitted by IBM researchers. So this algorithm was called Lucifer. Lucifer, and this Lucifer was itself was designed by a famous cryptographer called Horst. I don't know exactly how to pronounce his name. His name is called Horst Feistel, and he has designed a Lucifer family of algorithms sometime in 1960s. He designed a lot of algorithms. So this Lucifer was selected in the competition. So when the IBM researchers submitted the Lucifer, it was something like this. So the input is always 64 bits. The input is going to be 64 bit. This is the block size. Whereas the key was 128 bit. The key was 128 bit. Okay, this is the input plain text. This is the key K. Okay. Now, what NBS did was they want to analyze the security of this Lucifer. So they submitted this security to a secret organization called National Security Agency (NSA). This is also an American security agency. At that time, in fact, no one know that there is such an organization exists. Until in 1990, they finally found out there is something called NSA. Till that time, no one know that really it exists or not. So what NBS did was NBS contacted these fellows called NSA. They have the largest group of professional cryptographers in the world. Okay, at that time. So the NSA wanted to study the Lucifer algorithm, also the security of this algorithm, and they told some suggestion. For example, the design was changed to withstand the form of attack called differential cryptanalysis. In cryptography, there is a form of attack called differential cryptanalysis. We don't go into the details. So it was designed to withstand even the differential cryptanalysis attack. Okay. Okay. So they also suggested for some reason to change the key size from 128 to just 56 bits. I don't know for what reason. Maybe at that time The processor that was available was so less in processing power that it cannot handle 128 maybe. So some people think they wanted to break the algorithm, that's why they reduced it to 56. But we don't know because it happened sometime in 1974, right? That the processing power, everything was very very low at that time. So God only knows why they wanted to change it to 56 bit. So finally they took the Lucifer, they keep the input size to 64 bit. However, they change the key size. They change the key size from 128 to just 56 bits. Of course, your output is going to be 64 bits. Then they change the name of this algorithm from, initially I told you right, it's called Lucifer. Then they rename the algorithm to Digital Encryption Standard. That's how the DES was born. Okay. So after that, what the NBS did, what they published the entire specification of DES, including the bit level details. All the detail of the DES specification was openly published, and the American government Federal Information Processing Standard 46 was published. You know about the fifth standard, right? So fifth 46 was published for DES. So this is the very brief history of how DES came into operation. The interesting thing is almost from 1972 all the way up to 2005, it was used by it was in use. So it almost survived for a very long time, almost nearly 30 years, right? So it survived really for a very very long time, because until almost 1990 no attack was found. So later when the attack was found, they decided to stop the usage of this. So going forward, if you should not use DES in SSL TLS. When you use SSL TLS, you should never ever use DES algorithm. Okay. Although the NBS released the complete specification in 1977, certain parts still they did not tell till the end. For example, inside the DES algorithm, right, they use something called X boxes. It's called substitution boxes. We won't go into the detail. For example, why they chose certain parameter inside the substitution boxes, all those things they never disclose. Okay. So that's the brief history of DES algorithm. I told in 2005 the government announced no longer you should use DES. Okay. So roughly when the attack was started roughly around 1990s, they started knowing about slowly about different form of theoretical attack until finally it became practical as well. Okay. So the moment they came to know about attack itself, immediately they made another call for proposal. So it's called you all now that you all know the AES algorithm, right? So roughly sometime around I think 1999, they made another call for proposal to replace the DES with a new algorithm. So a lot of people were submitting algorithm for this particular project, and there were a lot of contender. Finally, AES was selected as a replacement for DES, but at that time there was one more algorithm came as a contender for DES. That fellow name is called triple DES. So next we will look at the very brief about triple DES. So triple DES is nothing but one of the contender for the AES algorithm when the competition was announced. Okay, when the proposal was announced. So triple DES internally is nothing but exactly the same DES. In DES what we saw, in DES I already told you, right, the input of DES, the plain text input is going to be 64 bits. The key is going to be 56 bits. Okay. So for the time being, let us first finish the DES discussion before we jump to the triple DES. Okay. So the output is also going to be, this is your ciphertext. Output is also going to be 64 bit. However, when you process internally, you also need 8 bit of parity bit. Although the parity bit is not used for encryption decryption, just for parity purpose, you also need this 8 bit of parity. So some people will say as 64 bit key size. This is wrong. The actual key size is only 56. The additional 8 bit is called parity bit. It only used for parity purpose. Inside the algorithm, it is not used for encryption decryption purpose. Okay. So you should never say DES key as 64. It is always 56 bits. Okay. Okay. So that's how the normal DES work. In triple DES, they use the DES algorithm three times. That means you need three different key. Key K1, key K2, key K3. All of the keys are 56 bits in size. 56, 56, 56. So the first variation of DES will look like this. You take the key, let's say this is your plain text, right? You take your plain text using key K1, you do the encryption. Then you take the output of this. Do one more time encryption using key K2. Now you take the output of this. Do one more time encryption DES using key K3. So this is the first variation of triple DES. But many people they did not prefer this algorithm because since the algorithm was new, they wanted a backward compatibility with the existing DES. That is, the same hardware should handle both DES as well as the triple DES. So for this purpose, they wanted a different variation of triple DES in order to support both DES as well as triple DES in the same algorithm. So what they did was, you first take DES. Let's don't use the word DES. You take the DES, you encrypt using key K1. Okay, this is your plain text. When I say encrypt, encryption is nothing but DES algorithm. Using DES algorithm, you perform encryption. Then you take the output of this. Now you decrypt this using key K2. Now take the output of this. You again encrypt using key K3. So this is the variation. Now there is a beauty here. What is the beauty? Let's say you keep the all the three keys same, right? K1 is equal to K2 is equal to K3. Then what will happen? Since you are first encrypting and then you are decrypting, because you are using the same key, these two will get cancelled. So it is essentially equivalent to encrypting the plain text using key K3. That means you are using this triple DES algorithm and all the three keys are equal will lead to your normal DES. So that's how they achieve backward compatibility with normal DES. So if you want real triple DES, use all the three key different. K1 is not equal to K2 not equal to K3. So if you do this, you will achieve the real triple DES. Okay. So in practice, you will only see this algorithm. This algorithm is also called EDE. The reason is first you do encryption, then you do decryption, and then you again do encryption. So the reverse is simple. The reverse is DED, right? So just the reverse you will do. So whenever you see triple DES in SSL TLS, almost always you will see only this format with the three different keys. Okay. Okay. When triple DES came, it became very popular for banking and financial application as well as for protecting the biometric information in the electronic passport. Even today, still triple DES in use, although if you use triple DES right, you will get slightly lesser rating when you subject your SSL server for rating, like the Qualys SSL lab rating, right? You will get slightly lesser rating if you use triple DES. Okay, next we will quickly see the security of DES and triple DES. We don't go into the in-depth details, just a very brief summary. We don't talk about the security algorithm, nothing. So in cryptography, the security of algorithm, let's say you have an algorithm, right? Let's say you have a plain text, you have a cipher text, and you are using a key K. Let's say you are using key as a whatever, in DES you are using 56-bit, right? So the security of an algorithm is defined in terms of bits. For example, let's say I say the algorithm is only provide 4-bit security. So what it means is maximum you need to, in order to break this algorithm, maximum you need 2 power 4 operation. So 2 power 4 operation is nothing but 2 times 2 times 2 times 2, right? 4, 8, 16. You need 16 steps in order to break that algorithm. So what is the definition of a step? The step can be anything. It doesn't matter. It can be a simple step. It can be a complicated step. It doesn't matter. So for simplicity purpose, they just say I need 16 steps to break an algorithm. So that's why sometimes you cannot exactly compare. Let's say two different algorithms, both offering 4-bit security, right? Since we don't know what exactly a step is, sometimes it might take longer time to break. It might take lesser time to break. But in effect, the cryptographer found this is a good thumb rule to quickly find the security of an algorithm. So using this notation, if we have to tell the security of DES, this 56-bit is not at all sufficient. Straight away you can perform what is called a brute force attack. A brute force attack is nothing but trying all combinations of key. For example, with the 56, you can have maximum 2 power 56 keys, right? You create a huge table of all combination of this key and then try one by one, and then finally you can break the key K. So DES is totally broken. Don't use DES. Okay. What about the triple DES security? Triple DES is still okay. Still the security is not that bad. So with the triple DES, the security I told you, if you use K1 is not equal to K2 is not equal to K3. Actually with triple DES there are three types of options in the standard. The standard say keyring is called keyring. Keyring number 1 means K1, K2, K3 are all different. Keyring number 2 means K1 is not equal to K2, whereas your K3 is same as K2. So in the first case you are using 56 into 3, totally 18 carry 1 3 5 15 16 168 bit key. In the second case you are only using 112 bit key. There is a third option K1 equal to K2 equal to K3. This is for the purpose of backward compatibility, right? I already told you. When you do this, it will become effectively DES operation. So this is called keyring option 3. So when people say I am using 3 DES in SSL TLS, don't use this, don't use this. You should only use this version. That is K1 is not equal to K2 is not equal to K3. Effectively your key size is 56 into 3, that is 168 bits. Even though there is 168 bit, there are certain category of attack. Using those attacks, you can bring down this 168 bit security to merely 112 bit security. Okay. So if you use this version, you will effectively it will bring down the security to 112 bit. However, there is another type of attack available. Using that attack, you can further reduce it to 108 bit security. So in effect, 3DES will only provide you 108 bit of security. It is still not that bad. So it is still is in use today. Okay. Okay. So we will stop here. So in today's episode, what we saw is we started with the remaining details about the RC4 algorithm. Then we learned about the block cipher. That for a block cipher, the input size is always going to be a block. The commonly used block size is 64-bit and 128-bit. Nowadays 64-bit is also not common, so most likely you will encounter 128-bit block cipher. We saw a lot of examples of block cipher like DES, triple DES, AES in Japan, Camellia, in South Korea, ARIA. Then we also saw Blowfish, Twofish, etc. Right? I also mentioned a brief story about the National Bureau of Standard in US that they, for the first time, they created a revolution by calling for a proposal so that they can publish the entire algorithm. So the security now no longer depends on the algorithm, it only depends on the key. Okay. In fact, there is a rule in cryptography called Kirchhoff principle. I always forgetting the exact spelling of this guy. Auguste Kirchhoff principle. The Kirchhoff principle says the security of the system should only depend on the key. It should not depending on the algorithm that you use. Even if you give the algorithm to the enemy, he should not be able to break the security. The security must only depend on the key K. That's what we mean by Kirchhoff rule in cryptography. So this proposal is following this Kirchhoff philosophy. So they openly asked for a proposal and finally chose the algorithm submitted by IBM. It's called Lucifer. Then they renamed the algorithm and it became standard, renamed to Digital Encryption Standard. So this fellow ruled almost for 30 years. Finally, when it was broken, they called for another proposal and finally choose another algorithm to replace DES called Advanced Encryption Standard. So several contenders came for AES. One of the fellow contender was called triple DES. So this is even still in use today. Even though we have AES, still in many places triple DES are in use. Effectively, DES totally broken by brute force algorithm. Whereas in triple DES, when you use all the three key as a different key, then effectively it will only provide 108-bit security. In fact, in many literature, you will only see 112-bit. But I found another paper where you can bring down the security from 112 to 108. Okay. So we will stop here. In the next episode, we will talk about the AES algorithm. Thanks for joining this lecture. See you again.